All right, so with NPSH, what you're looking at, if here's your pump. So there's the water surface. With NPSH, what you're looking at is the inlet side only. So you're just looking at that side. That's it, okay? So what you do is you take your atmospheric pressure, and generally speaking, atmospheric pressure is what? It's 14.7, but we're going to convert it into feet. So generally speaking, we get everything in feet, so it matches. So it's 34 feet. Okay, that's what you start with. That's your energy right there. And what's happening with your pump is you're creating a vacuum in the volute, so the atmospheric pressure pushes the water up the pipe, up the inlet pipe. Now you got to take off the static lift. That's how high your pump is set above the water. And that's a common problem, is having a pump set too high. Okay, it takes too much energy away from the water and the pump won't function properly. Okay, you take away your head loss, because head loss and static lift are the same thing to a pump. It doesn't really know the difference. And then you take away your vapor pressure. Okay? And then the vapor pressure depends on temperature, right? And there's a chart which I'll give you for that. So you got that formula down there, and then you've got those different values. Just remember that's only for the suction side, the inlet side. All right. Okay, different pump heads. Let's see, there's static and dynamic. Static is when you just lift water, you're just looking at the elevation you're lifting water to. And then dynamic is when you're actually pumping the water and you get head loss. Okay, horsepower, you got water horsepower, then you use efficiency to find brake horsepower and motor horsepower. And then electric power costs. Pumps in parallel and series. So what? Pumps in parallel, you double the flow without increasing the head. Pumps in series, you increase the head without increasing the flow. Pump curves we'll get today. Operating points, I hope we'll get to today. And then cavitation, which hopefully we'll get to Friday a little bit. All right, now the calculations you should be able to do is TDH and then NPSH. So TDH is for the whole pump. And what you got to do there is take the static lift, which is just how high you're raising the water, and then add in the head loss. Now the head loss is by far the more complicated of the two. So remember, when you get head loss, what you want to do if I can find this thing back here maybe. There we go. All right, now when you get head loss, you got the head loss for the pipe, and that's easy enough, right? But then you've also got the head loss for the fittings, and that's where it gets a little trickier. So what you want to do is find L equivalent, right? And here you've got L. So what you want to do to get the head loss is find the total L, okay? And that's equal to L for the pipe plus the equivalent length. Then find the head loss. So you got to remember to do that, okay? That head loss, you've got to find essentially one term for the pipe, which is just the length of the pipe, and another term for the fittings, which is the equivalent length of the fittings. Okay, and what that is L over D times D, right? So there are a few steps in getting the head loss for the fittings. All right, and then I'll also give you some horsepower calculations. And the horsepower is, again, lower right, GPM times head over 3960. That's all you got to do. Then you use the efficiency to get to the brake horsepower and the motor horsepower. Just remember to divide by the efficiency. All right, might have you find the operating point of a pump in a given system. So we might have you do that, and also might have you read some pump curves. We'll get to that stuff today, I hope. All right. Now, some of the other stuff that'll be on the test is force equals pressure times area. That's from midterm number 1. And flow rate is velocity times area, which is from midterm number 2. And then the open channel flow stuff will not be on there. So that chapter 15, you can just cross off. All right. So we good with that? We got any questions? I really don't want to do chapter 15. That's my impression.
John's going to do 15.
Oh, he is? Okay, good. Good. All right, why don't we have a look at pump curves? So pump curves are a graph that shows information about what the pump does. And have you all gone through these before at all?
Just in setting our own pumps, 50% is about the standard.
Okay.
Start with the stroke.
All right. All right.
But not.
Yeah. All right.
Not with the centrifugal.
Okay. All right. All right. Now, the thing to understand about a pump is for a simple pump, which is what these are made for, there's no throttle. You turn a pump on and it goes full throttle. Okay? And that's probably the most important thing to understand about a pump. There's no governor. You just turn them on and they go. So what determines how they act is the flow rate and how much head they're pushing against. Those are the two things that determine how the pump acts. You don't really set a pump to do a certain thing. It just does what it does. Now, you can get fancier equipment. You get variable speed and variable frequency drives to control pumps more. But a basic pump would just run and just do what it does. Okay? So there's a line that describes what a pump does. And that's this line that cuts down diagonally through the curve, TDH line. Okay? So here is what this pump is built to do. It has a certain amount of power. And what it's going to do with that power is lose some of it through inefficiencies, in how the pump runs. But basically what it does with the power is it splits it between head and flow. So if you push against more head, you get less flow. If you push against less head, you get more flow. That's basically how it works, okay? And so that's what that line there describes. So that's the basic pump curve. So you notice the x-axis is flow rate in gallons per minute, and the y-axis over there on the left, which is where we'd read it, would be the head. Now, there's some other lines on here, too, that we concern ourselves with. The first are efficiency lines. That tells you how efficiently the pump is running. So if I have this pump, what I'm going to want to do is run it right in there because that's where it's most efficient. I'm not going to want to put this pump in a situation where it's running down here because it's going to run inefficiently and I'm going to waste energy. Okay? Pumps are built to do certain things, so you want to use them where they are efficient. Okay? The other line you've got on a pump is the brake horsepower line. That's used to tell you how much horsepower the pump will use. In this particular pump curve, and they all seem to be a little different, you read that over to the right. So if you were running at this point here, your brake horsepower would be about 67. Okay. So let's say we're running this thing at 800 gallons per minute. What are the characteristics of this thing going to be if we're running there? So,
Depending on your headline.
okay, yeah. What type of head will this thing develop? 160 feet, right? Because I'm intersecting the TDH line over here. I go over that away. I don't know, about how many PSI is that? 0.433 PSI per foot? 70 PSI? Yeah, 64, that's a good guess there. 50, yeah, it's about 60, 69, okay. So that's 69 PSI. How efficiently will it be running? Yeah, 60, between 60 and 70, you know, and you can eyeball it as close as you want. I'd call it 64, but it's not like I got magic eyes or anything. It's somewhere in that ballpark, okay? And then what's the horsepower that it'll be using? No, here's the horsepower line, okay? 50. Okay. Okay.
So does that mean it'll use 50% of the rated horsepower?
Well, that means that, right, this thing is running about 64% efficient, so it's going to require 50 horsepower, and it's going to use 32 horsepower and put that to the water, because 64% of 50 is about 32. Okay? Now, why don't we check that out real quick? Horsepower is what? TDH? What's the TDH? $160. Flow rate is 800 gallons per minute. And then you got that magic constant you use, 3960. 32, okay? So the brake horsepower comes out of the motor and goes right to the pump, but it's not running, you know, that efficiently. It's 64% efficient. So that's what's going on there, okay? Doing all right with that?
So you could design a system where or kind of what pump, I guess, off this, or you would use this just with an existing pump?
Well, you can do both.
Yeah.
This just gives you information about it. All right, so for that static head example we did, we had a flow rate of 1,300 gallons per minute and a TDH of 139.4 feet. Where would this pump work well for that? So what I do there is plot that point up on the grid. See where it is. What page are we on there?
You just move 148. 148 for that one. Got it. Yep.
All right, and this is just that example we did. We got Q at 1,300 and TDH of 139.4. Yeah, 1,300, 1,400, so that's about here, right? Right about there, huh? See, that's pretty good. And how's the efficiency on that? That's not bad either, okay? So this would be a good pump to do that with, see? So I remember once I designed a little pump station there, and you know, they had software, and they pulled up the pump curves, and then I plotted up what the TDH was going to be, and you know, look for good matches, look for pumps that would work. So this one's pretty good, okay, for this situation. for that static head situation. Okay?
Are these pump curves made by the company, or is
Yeah.
it just a?
Yeah, the pump curve comes with the pump. The companies will make them. Yeah, and that's part of the package you get. You know, when you, if you have a lift station or any sort of pumping station, you should have an operating book for it, a manual that's put together, and the pump curve ought to be in there. Okay. Now, how about the other one we did where we had static lift, that was static head, this one. What would happen if we used this pump for that static head situation? Why don't you start by plotting that up? So plot the point up and see where it is. About there? Now, see, that's not a match, right? That ain't going to work. Very good. It's not anywhere near this curve. So what's going to happen if you hook this pump up into that system and turn it on, it's going to hit that point and just keep on going. It's going to start pumping more and at a higher pressure is what it's going to try and do. Okay? Because this pump is not built to do what that system curve there looks like, that red curve going down and to the right. This pump just isn't on there, okay? So it's going to start pumping higher flows. All right. So what I have there in red, this curve, the TDH curve, that's called the system curve. All right. Or no, my bad. That's the pump curve there. Now let's see what this system will look like as this pump starts pushing more water, okay? So what we're going to do here, we're going to realize that the pump runs on its curve. As the flow increases, the TDH decreases there. Now the pipe system, as you push more flow through it, as the flow increases, you get more resisting head, more head loss. Okay? So what you get for the system curve is a curve that curves up. What you have for your pump curve is a curve that goes down. Eventually they'll intersect, and that's where the pump will run. That's what we're going to look for, is that intersection point. Okay? So let's see what we got here. We had a flow of 1,300 gallons per minute. And the head loss per 100 for that was at 4.85. Is that what 1,300 gallons per minute is in an 8-inch pipe? Is it 4.85? That's kind of my recollection. All right. Now, what's the equivalent length of the system there that we calculated for that pump with static head? That would be back earlier in the chapter when we were working on that. The total equivalent length of that thing? It was back in that example that we did. It was back a ways. Let's go find it. It was this system here. All right. Okay, the equivalent length of that system was 304.6 feet right there. And I can't remember what page this was on. Did you all get that down? It was, what page is that? One.
Still looking. I'm not quite sure what it is.
I keep going. I think it's right. This one here.
That one?
No, it's the one before.
Doesn't look the
There we
same.
go.
Good.
That's pretty.
Okay.
Yeah, it's 134 or 304.6. It's near the bottom where it says total equivalent length of the pipe plus all fittings. Third one up from the bottom there on page 139. Okay, so page 139. All right, so the equivalent length of that piping system was 304.6. So what we have there for the fittings and the pipe itself is 304.6. So what we'll do is we'll take our head loss per 100 times 3.046. 304.6 feet is 3.046 100-foot lengths of pipe. So what we're doing there is finding the head loss. So we got 4.85 times 3.046. That's 14.8, let's say. Okay. And then what was the static elevation head on that thing on page 139? $36 feet?
Yeah.
36. So we'll add that in too. Come on now. Yeah, I know. Now we'll bring this thing back up. Okay, so we're looking at a flow of 1,300. The head loss per 100 is 4.85. The system head loss is 4.85 times 3.046. So that's 4.85 feet per 100 times 3.046 100-foot length. 14.8, thanks. Elevation head is 36. So the total head is what, 50.8? Okay. And that's how we got that point plotted up in the first place, okay? Which, of course, isn't plotted up here anymore, but right about there. Well, just a little bit off. Why is that? Did that bust something? $14.77 and 36. Yeah, 50.77. Okay, yeah, good. All right. Now let's try. Now what's going to happen if we run this pump is it's going to start pushing more flow than 1,300. See, because it's not on the pump curve yet. It's shooting a little low. So that pump's going to try and pump harder is what it's going to do. It's going to hit that point. It's just going to keep on going. How about 2,000? Okay. Let's see what that'll look like. So if it pumps 2,000 gallons per minute, what's the head loss per 100 for that?
10.64.
10.64. So we're going to have 4.85. No, we're not. We're going to have 10.64 feet per 100. and we'll multiply that by 3.046. And what are we going to get for head loss this time? 32.4, okay. And then we'll add that to 36, because that's just how high we're lifting the water. And we'll get 68.4. So that's the total head that will occur for a flow of 2,000. Okay. So when the pump gets up to 2,000 gallons per minute, it's at 64, was it? So that's about here. Okay. It's getting there, but it's going to keep going. Okay. It's going to say, it's just going to, it's still not, it can still do more, so it's going to pump harder. So let's try 2,400. Okay, so that pump's just going to keep going harder until it encounters too much resistance. That's the idea. So 2,400 gallons per minute. What do we got for head loss?
14.91.
14.91. So we're going to take 14.91 times our equivalent length. And what are we going to get there? 45.4. And we still got to lift the water 36 feet. So we're going to get what, 81.4? That's at 2,400. Okay. Yeah, we're a little high now, aren't we? Which is what we want, because, I'm sorry, no, I've got the wrong side here. Here we go. Yeah, we're right about on it. Okay, so that's pretty good. I think that thing's going to run at about 2,400 gallons per minute. That's what it's going to do. Okay, so the pump will just keep running until it hits the pump curve. That's the idea. Okay. And then when it hits the pump curve, of course, it stops. Now, is this a good place for the pump to be running at? No, efficiency is horrible, okay? So you don't want to use this pump to do this job. It's too overpowered. It doesn't run efficiently at this rate. It's going too hard, okay? It prefers more resistance. And, you know, what it prefers to do is this situation right there. So, you know, what's that? I'm sorry?
Trying to get that X to basically go over where your losses.
Yeah, you're trying to get the two curves to match each other in a place of efficiency for the pump that'll do the job you want done. Now, you know, if you got a pump that isn't running properly, you can kind of do some things. You can change piping arrangements. You could perhaps lower it a little bit if your MPSH isn't working, if you're getting some cavitation. You can, the other thing you can do for a pump, though, is you can start replacing impellers. Go with a larger, smaller impeller. That's a common way to modify a pump. But there might be cases where what you got just ain't going to do what you want it to do, you know. So, you know, you do at the very beginning when you're designing something like this, you want to design the pump so that it runs efficiently. Okay. All right, so Friday I'll go over pump curves a bit. And why don't you have a look at the rest of the problems in chapter 14 too, because they cover a little bit of reading pump curves. And that's what we'll do Friday. You might want to wait for the weekend to do it because we'll go over it a bit. There's a couple little tricky things with reading those things. And then there's one problem like this where you find what's called an operating point. Okay, so the operating point is where those two curves intersect, and that's where the pump will run. That's the last problem in the chapter, finding this point right here. Okay. All right, so.
We got the video up right now.
Yeah, I'll get that video up. What's that?
Good chance I won't be here.
Oh, yeah, sure thing. Yeah, I understand. You know, I'll get videos up for this stuff for sure. Okay.
67.